All right, great. Thanks a lot, Haim, for giving me the opportunity to share exciting news to you all. Um, it is possible to teach uh, Computer Science 101 in a university using JavaScript. So that's the big news. And to do that, we extremely shrink JavaScript. So this is joint work with Boyd Anderson, Lokok Lim, and Daryl Tan from the National University of Singapore. I'm at the moment on sabbatical from the National University of Singapore, visiting Uppsala University in Sweden. The goal: I want to teach CS 101 at the National University of Singapore, and we have 750 students, 3 professors in the team. It's a huge enterprise. There are 101 teaching assistants involved. We have extremely small classrooms that we call studios, so it's a big deal. The emphasis of this course is on mental models for computation. It's not necessarily a course where you're supposed to learn programming or where you learn developing software. It is the very fundamentals, computational thinking, and develop mental models for what happens when computer programs run. The good news: there is a textbook that fits this bill. It's called The Structure and Interpretation of Computer Programs. It's a computer science classic, developed at MIT by Hal Abelson and Gerald J. Sussman, and that is our textbook. Now, the bad news is that this book, or also called SIGP, is written using the programming language Scheme, and Scheme is outdated by now. It is not in popular use. We want to use a modern programming language. The students demand that they learn a programming language that is of relevance to them. So the goal is to use a modern language. Why do we use JavaScript? Now, Scheme and JavaScript have a lot in common. First of all, they have functions as first-class values. Scheme and JavaScript are dynamically typed, so they have that in common. And Scheme and JavaScript use automatic memory management like any other modern scripting language. This is not a coincidence. Brendan Eich, the inventor of JavaScript, wanted originally to embed Scheme in the browser when he was hired by Netscape to develop JavaScript. Well, they forced him to use Java syntax, and the rest is history. But these features he managed to establish in his browser language that he then called JavaScript. A turning point was ECMAScript 2015 for adapting this textbook to JavaScript. ECMAScript 2015 has block scoped let and const. It has a beautiful notation for lambda expressions, and it has proper tail calls as required by the standard. And that allowed us to adapt the entire textbook to JavaScript, and the outcome is this MIT Press published book called Structure and Interpretation of Computer Programs, JavaScript edition. So we proudly announce that we have now this classic textbook available in our favorite programming language, JavaScript. Now, what's the problem? What is the story of this textbook? The textbook starts with functional programming. Functions start out in chapter 1 of the textbook. Chapter 2 adds data structures. Chapter 3 then adds state assignment for the first time, and chapter 4 then develops an entire interpreter for such a language and explains what happens when computer programs run by showing the students how they can write an interpreter. Chapter 5 is on compilation that I won't talk much here. What is the problem? The problem is JavaScript is too big for teaching a course following this textbook. The textbook doesn't say anything about object-oriented programming, so the entire object notation of JavaScript, classes, methods, new, that's all extra noise that we don't want to deal with in this course. There's also a lot of idiosyncrasies of JavaScript that we want to avoid, and so our strategy here is to shrink JavaScript to the bare essentials. We start out, and the shrunken versions of JavaScript we called source. So source chapter 1 is a version of JavaScript that is basically shrunken to only the constructs needed for chapter 1 of the textbook, which is what we call the lambda calculus, basically functions and function applications, plus a statement-oriented syntax, some primitive values, explicit recursion. That's all. Chapter 2 adds data structures, and what we do is we add pairs. Chapter 3 adds assignment. Chapter 4 adds a parse function, only what is needed for this textbook. So let's take a look at source chapter 1. Source chapter 1 is a minimalist programming language. To give you an idea, here is a classic computer science example program from the first few days of a course. A factorial function, a function that computes the factorial of a given number. So here, factorial 5 is 120, and this is the environment that we developed for teaching this course. We call it the Source Academy. And it lets you choose the sublanguages that you want to use. It also allows us to force students to use particular sublanguages in the assessments. The mental model for such a functional programming language is called a substitution model. You just substitute expressions when you can by the simpler form. So for that, we developed a stepper tool. So here is the execution of this program using the stepper tool that we developed. So here you can step through this program step by step, and finally you see the final result of 120 appear. That should give you an idea of how our students experience JavaScript and how our students experience this sublanguage of JavaScript. Now, if you want to do things that are not in the sublanguage, let's say you want to let x equals 3, you try to press run, what you get in the system is line number 11, mutable variable declarations using let is not allowed in the sublanguage. So we force the students to use only the sublanguage, which is, as I said, minimal. So you have function declaration, you have constant declaration, no let, you have conditionals. Basically what you would expect from a small language that lets you do functional programming. Expressions also minimal. You have binary and unary operation, function application, lambda expressions, and the conditional expressions using question mark colon. To give you an example about the fun things that you can do in this programming language, source chapter 1. Here is a little graphics example. We call this rune programming. So here is a little import of some library functions, and we can load an image from a website and apply the function show to it. Now, this little domain-specific language, if you want, allows us to stack two images on top of each other. It allows you to put two images beside each other. And with that, you can already do interesting recursive programming. So instead of this factorial function that you have seen, we can let our students have fun with this. So for example, you can visualize recursion here. So you can program a recursive unfolding, a sort of a fractal image that you see here on the screen. So that gives you an example of how we can make use of the power of web programming for the benefit of our students. Source chapter 2 adds data. Also in a minimal way, we add null for the empty list, and we add a pair head and tail that correspond to schemes, cons, car, and cutter. What we can do with this is higher order functional programming using map reduce filter, for example. And to give you a glimpse of what we do then with this language, let me show you what students come up with. We introduce sound processing in this course, and I'll give you a little idea of what students can achieve when they use sound processing in the browser in this programming environment called Source Academy. So here's a little example, and I'm running this program. It is a competition entry by the student Siddharth in 2019. And here you hear the output. I hope you can hear this.
We hear that.
You hear it?
Yeah.
Oh, that's great. All right. And I hope you recognize the song, anyone? Okay. So this is basically using list processing, all done using list processing in this sublanguage of JavaScript. Source chapter 3 adds state. So SIGP's chapter 3 adds assignment constructs. We have a tool to let you see what happens when computer programs run that use assignment. This substitution model doesn't work anymore, so you need to do something else. We call that the environment model, and we have a tool that lets you visualize what happens when programs run that use assignment. This environment model lets you see the connection of the different declaration and what happens at runtime, the frames of environments that get created at runtime. What can we do with this language? Let me show you a little motion detector that our students programmed for that uses video processing. So we have the ability to program video filters with a given input frame and a given destination frame. And with that, we can very easily program a motion detector. So to give you a little demo of that, so here is a very small program that uses video processing using web technologies to let our students do fun stuff. All right, source chapter 4 adds only a parse function. I may not have time for showing you the meta circular interpreter. I may have some time for that. So let me show you what source chapter 4 does. Source chapter 4 is a language that has a parse function. So you can write parse and you give to the parse function a JavaScript program. So parse const x equals 1 shows you how we can represent programs using a data structure. And if you want to see this in a list notation, we have a function display list, and you can see that here that we are representing this program using a list that has a tag called constant declaration, and that has two components. One is a name, and the other one is a literal value, the value 1. So that is a way to represent programs, and with that, you can write an evaluator in this language, in this source language, sub-language of JavaScript, an evaluator for programs. So this component is a program, you check what kind of program it is, and you do the right thing to the environment that you're passing as an additional argument. So here, as an example, we parse and evaluate the factorial function that you have just seen, and you can run the evaluator that our students programmed then in the source academy itself. And you see here the value 125 is now the result of evaluating this program using this evaluator programmed in following the textbook chapter 4. That should give you an idea of roughly how we are introducing our students to programming in this course that uses JavaScript. Now, you've seen the Source Academy. The Source Academy is a free software, free as in freedom. So you can look, you can play around with it by cloning this GitHub repository. And It is developed for students by students. So if you look at the top right, you see here our Hall of Fame. These are all students who developed the system. So there are by now about 160 students who have contributed to the development of the system since 2018. Okay, so that was a wrong move. The Source Academy itself, sourceacademy.org, what you have seen so far is a serverless system and deployed using GitHub Pages. We have an extension of the system that we call Source Academy at X. It allows schools, universities to run courses following this textbook and using the system. And that Source Academy at X adds a scalable backend written in Elixir, a motivational game, achievements. So it allows you to run a gamified course. It allows students to upload assignments. It allows teaching assistants to manually or automatically grade students' assignments. It allows you to run programming contests, such as the sound contest I give you a little demo of, and it has lots of course management support. This Source Academy is actually a programming language lab. It has in-browser language implementations. The parser, we use JavaScript's Acorn parser, our version restricts students to the chosen sublanguage of JavaScript. Our workhorse implementation is a transpiler from JavaScript to JavaScript that allows us to implement proper tail calls, even if the underlying system does not support proper tail calls, is not ECMAScript compliant. And we add pedagogical error messages in this transpilation process. The stepper tool is another language implementation that you have seen. Our environment model visualizer that you have seen is also a language implementation based on an interpreter. And we have compilers for what we call the source virtual machine language that allows us to run robotics on Lego Mindstorm robot kits in this course. The outcome, the approach to shrink JavaScript for Computer Science 101 is liberating for everyone involved. Students are liberated because even beginner students who don't have any JavaScript background can start from first principles and very quickly achieve what their expert programmers can achieve, because the language is very, very small. Instructors don't need to worry about language features that we don't want to cover. We don't want to cover object-oriented programming in this course, and we don't need to discuss it because it's not even possible for students to use objects in these sublanguages. The implementers of our Source Academy are liberated because they can design and implement new tools for the system in semester projects, and that would not be possible if the language would cover the full language of JavaScript. The Source Academy is very popular among students. They strongly agree that this system helps them understand the structure and interpretation of computer programs. And here is some anonymous feedback from our students. They say it's a brilliant platform, nothing short of a marvel, and so on. In conclusion, JavaScript for Computer Science 101 is possible. That's the good news. ECMAScript 2015 was a game changer for this approach. It enabled a seamless use of JavaScript in an SIGP-based course, and it allowed us to fully adapt the entire textbook to JavaScript, and the result is the MIT-published SICP JavaScript edition. So, JavaScript works for Computer Science 101 if you shrink it. Thank you.